All right, let's absolutely conquer chemical equilibrium in just 8 minutes. You know this is a top-scoring topic for JEE Mains 2026, and we're about to break down all the essential laws, formulas, and tricks you just can't afford to miss. Okay, let's dive right in. So first up, what even is equilibrium? I want you to picture a perfectly matched tug of war. You've got the forward reaction pulling reactants to become products, and at the same time, the backward reaction is pulling those products right back into reactants. Well, equilibrium is that exact moment when the rope stops moving, not because the teams gave up, but because they're pulling with equal and opposite force.
And here's the thing you really got to get. At equilibrium, the amounts of reactants and products become constant, but, and this is a big but, they are not necessarily equal. Think about a really busy store. The number of people inside stays about the same, right? But that's only because new people are walking in at the exact same rate that other people are leaving. It's a constant flow, not a frozen picture.
Yeah, this is probably the biggest misconception out there. Equilibrium isn't when the reaction is over. It's when it's just perfectly balanced. On a molecular level, it is organized chaos. Reactants are constantly becoming products, and products are constantly turning back into reactants. It's this nonstop, perfectly choreographed dance of molecules. So, if it's this balanced dance, how do we actually, measure this state of balance? How do we put a number on it? Well, that's exactly where the equilibrium constants Kc and Kp come into play. Let's take a look at how we can express this perfect balance mathematically.
Writing the expression for Kc is actually super simple. It's just a ratio. You put the products over the reactants. You just take the molar concentration of your products, raise each one to the power of its coefficient from the balanced equation, and then you divide all of that by the concentration of your reactants, which are also raised to their coefficients. That's it.
Okay, now let's talk about a key difference here. Kc, which uses molar concentrations, is perfect for reactions happening in a solution. But when you're dealing with gases, it's often way easier to measure pressure, and that's exactly why we have Kp, which uses the partial pressures of the gases instead. It's all about using the right tool for the job.
And you want to know the best part? You can easily convert between them with this incredibly useful formula. Kp equals Kc times RT, all raised to the power of delta Ng. Here, R is the gas constant, T is your temperature in Kelvin, but the most important part is that delta Ng. That's just the change in the number of moles of gas. All you do is subtract the moles of gaseous reactants from the moles of gaseous products.
This simple table right here, it's a total game changer for multiple choice questions. If your delta N is positive, which means you're creating more gas molecules in the reaction, Kp is going to be bigger than Kc. If it's negative, Kp will be smaller. And what if the number of gas moles doesn't change at all? Well, then they're exactly equal. This is a quick mental check that can save you a ton of time on the exam.
Listen up, because here is a golden rule you have to remember. Pure solids and pure liquids are basically invisible to the equilibrium constant. Why? Simple. Their concentration is constant. It just doesn't change. So we just treat their value as 1 in the equation, which means we pretty much just leave them out. Don't let them trick you on a question with this. Okay, so we've got this perfectly balanced system. But what happens if we poke it? What if we mess with it? That's where the brilliant Chatellier's principle comes in. I like to think of it as the ultimate rule of chemical rebellion. Whenever you try to change a system at equilibrium, it fights back. The principle itself is pretty simple. If you apply a stress to a system, the equilibrium will shift to relieve that stress. I want you to think of it like a chemical seesaw. If you push one side down by adding something, the system's going to immediately work to bring the other side up, just to restore that balance. So how can we become the master puppeteer of this balance? Let's look at the 2 most common ways to deliberately shift an equilibrium: by changing the concentration of substances or by changing the pressure.
Let's start with a quick thought experiment. So, we have our system just sitting there in perfect equilibrium. What do you think would happen if we suddenly just dumped in a whole bunch more of one of the reactants?
Well, the system's immediate reaction is to get rid of it. It's like we just added a huge weight to the reactant side of our chemical seesaw. To rebalance, the equilibrium shifts forward, over to the right, and it starts consuming that extra reactant to make more product, until a new, stable equilibrium is found. All right, now let's talk about pressure. This one is a big deal for any reaction that involves gases. So what happens if we suddenly crank up the pressure on the whole system? Let's say by squishing the container into a smaller volume. To relieve all that extra pressure, the system is going to shift to whichever side of the reaction has fewer gas molecules. Just think of it like a crowded room. If the walls start closing in, People are going to naturally move to the less crowded side to make more space, right? All you have to do is count the moles of gas on each side of your equation, and you'll know exactly which way it's going to shift.
Okay, now for the moment you've been waiting for. Let's get into the high-yield shortcuts and exam tricks that are going to give you a real edge on those JEE questions and help you lock in those extra marks.
This right here is the ultimate secret weapon for predicting which way a reaction will go. You compare Q, the reaction quotient, with K, the equilibrium constant. See, Q is like a snapshot of the reaction right now, and it's calculated the same way as K. If your Q is less than K, it means you don't have enough products yet, so the reaction just plows forward. But if Q is greater than K, you've overshot the mark and have too many products, so the reaction shifts backward to get back to balance.
Okay, time for a rapid-fire round of key tricks. You ready? If you add a reactant, it shifts forward. If you remove a product, it also shifts forward. If you increase the pressure, it favors the side with fewer gas moles. And the classic trick question, what happens if you add a pure solid or liquid? Absolutely nothing. No change. Don't you fall for it.
Whew, okay, that was a lot of information in a very short time. So let's lock it all in with a super fast recap of the absolute most important points that you need to walk away with. Here are your 4 key takeaways. Number 1. Equilibrium is dynamic, a non-stop dance, not a dead end. 2. Kp and Kc are linked by that crucial formula. Kp equals Kc times RT to the delta Ng. 3. Le Chatelier's principle just means systems will always fight back against any change you make. And 4. When you increase pressure, the system finds relief by shifting to the side with fewer moles of gas. Got it? Good.
And there you have it. That is your crash course on chemical equilibrium. You now have the core concepts you need to go out there and tackle those high-scoring questions with a ton of confidence. Make sure you download the notes from the description for a quick review before your exam.
Hey, if this power revision helped you out, do me a favor and hit that subscribe button for more 8-minute deep dives. Next up, we are taking on the challenge of ionic equilibrium. I'll see you there.